Been doing a lot of maybe some high school trigonometry and some little freshman calculus in this class. I'm going to take you back even further right now. We're going to talk about dishes. And the way to start talking about dish antennas is to start with the parabola, the thing that you probably learned early on in high school. Let's review, because this is important. The parabola takes the following form. Y equals x squared over 4p. P, okay, that basic parabola looks like this when you graph it on the board. It goes through the origin, symmetrical on both sides of the y-axis. That value p is a particularly important value. It is the distance from the origin in this particular configuration to the focus. The focus. Now, if you recall from high school geometry, the way you define a parabola, the parabola has a geometrically significant definition. It has a mathematically significant definition, but there's geometrical meaning to it as well. If you take a line that is parallel to the x-axis, any line, we call that line a directrix. Then any point from that focus, if you draw it to any point on the parabola and then straight up to the directrix, it turns out these path lengths have all the same distance. So even if I go straight up like that, all the same total distance. Not only do they all have the same total distance, but it also turns out that angle of incidence is equal to angle of reflection, which means that if I point a radiator at the focus of this parabola, and then what's more, I turn it into a paraboloid, a three-dimensional surface, by taking the parabola and revolving it about the y-axis, then whatever radiating element I put at the focus, any path that I draw from that element to the surface of the paraboloid, and then draw straight up to a plane of directrix, no matter what beam I shoot out, which direction I pick, if I follow those rules, I always travel the exact same path length. Now, that's really good for us, right? Because that means if we put a radiating element there, a simple electromagnetically small antenna, like, say, a half-wave dipole, and it illuminates a parabolic reflector, all that wave emanates, it starts out in phase, and if it's all traveling the exact same phase length, when it gets to that plane of directrix, it will all still be in phase. And so one way to think of a paraboloid is that it converts a point source into a plane wave in a very short, relatively short distance traveled. It's a wave converter. So now, if you have a circular paraboloid, and that's by no means the only type of paraboloid you can use, but if you have a circular paraboloid and you illuminate it with a broadbeam horn or a helical antenna or a half-wave dipole or whatever your antenna of choice is, that in the front of it, as you move across the surface of the antenna, you will see an approximately uniform in-phase field. And the in-phase is the most important part, because that's what gives you constructive interference along the bore site of your antenna. But you'll see basically no field outside the front of the aperture, and then it'll start to ramp up, become roughly uniform, and then ramp down. So even though it was a very academic problem that we just worked with the uniform circle, dish patterns look strikingly like that, no matter how good or how bad you make them, it turns out. Really, at a certain degree, the quality of the dish antenna has more to do with things like, a fractional gain of peak gain in your main direction and maybe dithering with the side lobes, as you'll find out on your assignment. doesn't change that overall behavior of main beam and lots of little side lobes. Yeah?
So is that the flash
And this works the same way. They focus the light, the reflected from the paraboloid, right?
Yeah, if you have an optical parabolic reflector, it works on the same principle. And the reason is that these are electromagnetically large structures. You don't make parabolas typically paraboloids that are only a couple wavelengths across. They're radii of 5, 10, 15 wavelengths or larger. And when you do that, you can use geometrical optics to approximate the wave propagation. That's where you use ray tracing, basically. Ray tracing says that the wavelength is small relative to the surfaces that I'm encountering. And in that case, I have these smooth surfaces. I can use angle of incidence equals to angle of reflection. I can track phase just by studying the geometrical path length of these rays that I've traced. And guess what happens? You get these beautiful formulas that turn out to be broadband. A parabolic reflector is actually pretty broadband, as long as it's more than a few wavelengths of radii, 10 wavelengths in diameter. It will essentially work for any element up to a point that you place into the focus and excite. And it works the same as a reflector in both receive mode as in transmit mode. The same principle of reciprocity holds. If you put a source and use it as a transmitter, it will focus very tightly and transmit most of that energy along bore sight. If you put a receive antenna on the focus, the same principle holds. It will be very good at collecting with high gain the energy coming in from a certain direction, that power along bore sight. Not very good at all at receiving stuff that's off axis. Again, reciprocity at work. So, with that in mind, let me give you a little category of several types of reflectors that you'll find in satellite communications. We have your classic front-fed reflector. And this looks like this. You have a parabolic reflector, and it's usually circular. So this is a paraboloid, and the paraboloid kind of goes up to infinity in terms of its mathematics, but you slice it right across in the XY plane or parallel to it. And somewhere, wherever the focus is, you put your feed element. And there's usually some mechanical arm for mechanical stability that holds the feed element in place and also allows you to run some cabling down. Now, the front-fed reflector is still very common, a very useful type of antenna, very easy to build. What would be one of the drawbacks of using the front-fed reflector? You losing coverage. How so? Yeah, that's right. It's casting a shadow. If it casts a shadow in optics, it'll cast a shadow in RF. And you'll lose some efficiency. Some of the wave that comes in here will scatter off the arm and off to the side. It's not a tremendous amount, but every little bit helps with the dish. And you are giving away some of your gains. Not only that, but you also have to route your signal now, which could be very high frequency. Remember, we use millimeter waves and higher in satellite communications sometimes, upper end microwave frequencies. Those are very lossy to transmit on a coaxial cable. So more often than not, you'll have to put a low noise block converter there by your feed element and convert it down to a lower frequency, which means you got to run power to this now and all this other stuff. And now that also means that you've got some sensitive microwave and millimeter wave electronics just sticking out there on the arm, up in the air. Lightning can strike it. The birds can poop on it. The sun will shine on it and burn it up. It's exposed to the elements. So, what other alternatives do you have? Well, there's a couple ways to deal with this problem. One is to use an offset feed or an offset fed reflector, where instead of taking a nice circular cut of the paraboloid, let's say I had that same paraboloid Now I'll just cut a different section out of it. I'll still put the focus at the same place, but now my feed arm no longer blocks my direction of peak gain. So in other words, the power is going to come down here, and it'll still all focus at that same focal point. Now again, I still have to have probably a block converter or some sort of low-loss cabling, which could be dicey. But that's a nice way to handle a dish antenna. And in fact, many of you that have satellite TV at home probably have an offset fed dish. You can always tell because the arm is and the feed is kind of off to the side. It doesn't block your dish unit, which is not always a circle anymore. It's now kind of an oval or some irregular shape that they've cut out of the paraboloid. Now, another form is that these are two different strategies where you put the feed in front. Now, some clever person came up with an idea of using a sub-reflector. They said, well, we reflected it once. Why can't we reflect it again? So let's say I have a paraboloid, this time a circular paraboloid, like the front fed reflector, but then I put a sub-reflector. And in this case, I've got a convex sub-reflector. So if I design the shape of the sub-reflector right, my wave comes in, bounces up here, and bounces to the center. This wave comes in, comes over here, bounces to the center. And what I find is that I have this new focal point on the back side of the antenna. So I have to accept actually a little bit of loss here because that subreflector is going to shadow, say, 10% of the area of my dish antenna. However, I get a nice clean transmission of everything to this point, and I can actually dump this straight into a waveguide. So whatever you've lost up here on the subreflector, you usually more than get back in the losslessness or the low lossiness of the waveguide or whatever structure that you've put behind the dish, which now conveniently is out of the elements. It's a much shorter run usually to your transmitter shack. You can put your low noise block converter here out of the elements if you wish, even still. And this is a nice way to do parabolic reflector antennas. In fact, this particular configuration is called a Cassegrain antenna, a Cassegrain sub reflector antenna. And there's another variant of this one where you use a concave subreflector. This is called a Gregorian dish. I did not invent this. But it's the exact same principle otherwise. You collapse everything to a point there, and you route your signal out that way. Any questions? Any comments? Seen some of these in practice. There's a really nice sub-reflector dish up on the top of Van Leer if you ever get up to my office and peek out the window of the 5th floor. I believe that was one of Professor Steffes' installations from years ago. A nice big dish out there. Now, there are variations on these as well. In fact, I saw once a very clever variation of this. It used a dichroic sub reflector. So it was a Cassegrain antenna. So it had a sub reflector there. But instead of making the sub reflector out of solid metal so that it would reflect everything, they used a pattern of metal that was a frequency selective surface. I don't know if you're ever familiar with any of these types of things, but if you take a pattern like circles or crosses or squares, or there's a million ways to make these things, but you change the size and the spacing and the thickness of the square or whatever shape you're tessellating across the surface. You can make a surface that is a frequency selective reflector. That means at some frequencies, the wave will hit it and bounce right off as if it's a perfect reflector. At other frequencies, it's almost, due to resonances, the wave will pass right on through. And it's really interesting, depending on the shape and how you lay these things out, you can make low-pass filters, high-pass filters, notch filters, band-pass filters, the whole complement. And so I saw once an installation where they put a dichroic sub reflector here, which allowed at one frequency to come in, reflect off the sub reflector, and go down to a point here, like say the high frequency. And this was a broadband satellite that was being used for lots of different types of satellite transmissions. Then there was another feed at the focal point here behind the subreflector at lower frequencies. This frequency selective surface allowed those low frequencies to pass right on through and go into that feed point, which then was routed separately through two separate hardware. And the principle that they were exploiting there is that when you're trying, the dish itself, of course, is broadband, right? You can probably go down into the hundreds of megahertz for some of these big dishes and all the way up into millimeter waves. And if you want to use it across that band, the hardest part to make broadband is both the feed and the low noise hardware, RF hardware, that you attach to those feed points. And so once it hit the reflector, it was more beneficial for a highly sensitive Earth station to then route those signals to two different feeds and two different RF chains. You get less loss, more signal fidelity that way. So I thought that was an interesting variation on a parabolic reflector, the Cassegrain reflector. Okay, so those are the types. Now, I've presented this from a very Earth station-centric point of view. Keep in mind that spacecraft also use reflective antennas. Parabolic reflectors are very common because they also need gain both to receive and to transmit, particularly those that we put in high Earth orbit, geostationary Earth orbit, or space missions that we send to other planets outside of Earth orbit. Now, dishes on Earth are very heavy, bulky things. They're not particularly practical to send up into space. So many of the types of parabolic antennas that you see on spacecraft unfurl. They'll start up as a very collapsed structure, and they'll have a netting on them. Sometimes the netting is almost like a gold mesh. And so it unfurls, it kind of pops into parabolic shape. And if it's a kind of a gold mesh, then it's a nice reflective sub-reflector, and you can use that for communications back to Earth. I've even heard of satellites in some instances that unfurl, they don't even use a conductive reflector. It unfurls into a parabolic position, and then there's literally a little spray nozzle that sprays a metallic conductor onto it that hardens it into place once they're assured that it's deployed properly and becomes sort of instant dish. Instant dish. Well, one of the coolest parabolic reflectors I ever saw was an inflatable one. It was actually for the use of soldiers in the field. They were working on it over at GTRI. It looked like a whoopee cushion. It was a big whoopee cushion. You blew it up, and if you put the right pressure in, it popped open, and one side had a reflective coating on it, and it was parabolic under this one pressure that you were supposed to inflate it to, and you'd have an instant Earth station that you could talk with on the ground. Just pop it down with a little tripod, point it to your satellite of choice, start communicating with reasonably high gain. They put a conductor on one side, and on the other side, they had this sort of opaque material. I asked them, well, why didn't you make it translucent? And they said, well, there's a problem that some dish antennas have that you have to always be aware of. That is, if the sun passes in front of your dish, you could incinerate your feed if you're not careful. So, for example, if you have a nice shiny metal reflector, or even one that's painted white, and the sun just happens to pass right into the main beam, and all of that solar energy, remember dishes are broadband, even up at the nanometers of wavelengths, that energy collapses onto a focal point, and you can often wind up melting your feed antenna if you're not careful. So you always want to put some diffusing paint on your dish antenna. Don't make it shiny. Don't try to make it look all cool. Paint it black if you have to. Now, the biggest dish antenna, the biggest Earth station dish antenna, I think the biggest static reflector is that one in Arecibo, Puerto Rico. But the biggest movable dish antenna is actually in West Virginia. Has anyone ever been to the Green Bank Radio Observatory? It's literally in the middle of nowhere by necessity, right? Because they want to do these sensitive radio measurements. And so they put it up in the mountains of West Virginia, surrounded by mountains and nothing else. And so even if you're close to it on the map, it still takes hours to get to it. I remember I went there once. I was driving. I looked on the map. It looked like it was about an hour away. It took me 5 hours to get there. There's no main roads, no nothing. But that's what they want. They want radio silence in that area. And the main dish at Green Bank is an offset fed dish that I believe is about over one football field wide, about 100 meters in diameter. It has an offset feed here. And this thing can turn and point. It's really quite a sight to behold. The thing is so large that the subreflector is actually composed of a lot of carefully actuated panels that lasers use. You use laser measurement to figure out exactly where in space each panel is, because this thing is so large that the structure deforms slightly as you rotate it, and it can actually compensate for that deformation as you bend it around. It's really cool. Very good nerdy little field trip if any of your friends are up in that part of the woods, literally. And that's at Green Bank, West Virginia. Okay. Now, where do inefficiencies come from in a dish? So we said that our peak gain is going to be equal to 4 pi over lambda squared times the physical area of the dish. Times, in reality, a number that is going to be less than 1 that represents the efficiency of the dish, the radiation efficiency. And that efficiency is going to take a variety of forms. In fact, here's a really useful rule of thumb for just about any aperture antenna, whether it's a really big horn or a reflector, even in an array, it's really not too bad. Peak gain is approximately equal to 30,000 divided by the half-power beam width with respect to theta and the half-power beam width with respect to phi. It's a very useful engineering formula to keep in your back pocket. These are in degrees, by the way. This is more of an empirical formula, a rule of thumb, and so it's in the useful units of degrees. This is linear gain, not in the dB scale. And for things like a circular aperture antenna, as we saw in our radiation example, theta half-power beam width is going to be approximately equal to phi half-power beam width. This formula, the way it's expressed, always assumes that you have the dish oriented along the x-axis, so that you have a theta half power beam within elevation, and then also a phi half power beam within azimuth. So if you just kind of tilt the problem that we studied at the beginning of class onto its side, you basically have this orientation. There's going to be a half power beam with this way and a half power beam with this way. And that example was radially symmetric, so they were exactly equal. For a realistic dish antenna with a realistic feed element, realistic polarization effects, et cetera, this is approximate, but it's a really good approximation. And so this actually gives you a really nice estimate of what a realistic aperture antenna will produce if you want a certain half power beam width. If you want to be able to cover, say, a spot angle this big, 4 degrees here, 4 degrees there, then you plug in that here, 30,000 divided by 16, and voila. That's probably the peak gain that you're going to get out of the system, because they're related. The higher my peak gain, the narrower my beam gets. So that's a useful formula to keep in your back pocket. Where do the inefficiencies come from? This kind of takes into account some of those typical inefficiencies already. You may be able to do better than this. You'll probably do this or a little worse in practice. Where does that a little worse come from? The first one is polarization. So let's say that I'm trying to make linear polarization. I've got a dish here. I've put my transmitter feed element out in front at the focus. I illuminate it. And I want to achieve perfect vertical polarization. Well, it would make sense to start with perfect vertical polarization at my source. However, this vertically polarized source, when it strikes the curved dish, may depolarize slightly. And so you will lose a few percentage points of your inefficiency due to the polarization twisting of the antenna. That's one thing. Another source of error is something called aberrations. And this is the part that's highly frequency dependent. If there's no such thing as we can't make a perfect parabola, right, or a paraboloid. At some level, at some scale, due to manufacturing processes, you're going to deviate from a parabola. And that's going to cause a little bit of phase error, which is going to mean that you're not going to perfectly constructively interfere. There's going to be some imperfect constructive interference. You're going to lose a little efficiency in that manner as well. Now, how do you test for aberrations? It's a really clever test what you do. You set your parabolic reflector up here before you paint it so that it looks like shiny metal. And you put a light bulb at the focus. And then you walk to the other side of the room after turning the light bulb on and you look at it. What you should see when you look at your reflector is a nice, well-lit, uniform beam of light coming out of there. If you see any spots that are a little darker than others, then you know you have an aberration, a slight deviation from the true parabolic curve. That typically affects all frequencies. What affects the maximum frequency often that you can use a dish is the surface roughness. So again, this is actually just another type of deviation from the true parabolic shape, but it occurs at a small scale. Think of it not as a dent, but as literally roughness. You put your hand over it and you can feel roughness. Surface roughness, at some scale, when a wave strikes a surface that has roughness on it, if that roughness is electromagnetically small, even if microscopically you can see hills and valleys, the wave will pop off that thing as if it were smooth. However, as you get smaller and smaller in wavelength, you get more and more diffraction. so that the wave that comes down now starts to scatter in off-axis directions, directions where angle of incidence does not equal to angle of impedance, incidence. Angle of reflection does not equal to angle of incidence. That's called non-specular scatter. And that obviously robs energy out of your specular direction where you're trying to get this nice constructive interference. That will also produce a little bit of inefficiency for the desired frequency that you're using. As you start to go up in frequency and the wavelength gets smaller, there's a threshold called the Rayleigh Limit, the Rayleigh Criteria, where the standard deviation of height sigma sub h, so that would be if you had the true parabolic line running through here, what is sigma sub h, the standard deviation of the height from that line. When that gets to be greater than lambda over 8, that's when you start losing power due to surface roughness. So as soon as that deviation becomes lambda over 8, you start shedding a significant amount of your power, a measurable amount of your power in off-specular directions. Very good, useful rule of thumb to put in your back pocket. You'll probably see it again. The Rayleigh criterion isn't all bad, though, right? What it really means is that you can get away with a lot if you're not anticipating using the dish antenna up at millimeter waves or some high frequency where the roughness is an issue. So, for example, instead of a solid piece of metal, you just use some mesh as your reflector dish. This is a great thing to do, right? Because mesh, it's nice. You can make it parabolic. It won't have any aberrations if you set it up right. And the little holes that you've put in the metal to make the mesh, if those holes are less than a lambda over 8, then you pretty much have satisfied the Rayleigh criterion, and most of the energy is going to reflect at your desired frequency. But, of course, you save a lot in weight. And you also, this is probably even more important, you've saved a lot in terms of wind shear. One of the problems with dish antennas is they act like giant sails. And so if you have a really big dish, the proper thing to do is to stow it facing straight up when you're not using it. Tip it to its side when start tracking when you are using it. And that's not a necessity when you have a mesh-shaped antenna. If you want an entertaining movie about dish antennas, believe it or not, they've actually made one. Has anyone ever seen The Dish, that movie? So it's a really funny story. It's kind of a quirky little comedy about this dish antenna down in Australia. So it turned out that the way that the Apollo mission panned out, when Neil Armstrong was going to do his first walk on the moon, and that this was going to be live broadcast all over the world, it turned out that the moon was going to be on the moment that he stepped off, when everything was planned, the moon was going to be on the opposite side of the Earth from the United States. And you're at the moon, time is of the essence. You can't just sit around for 12 hours and wait for the moon to come back into phase. So the only people that could reliably detect it were in Australia. And so NASA contracted this big radio astronomy dish in sort of the middle of nowhere, Australia, to receive the very first pictures from the moon. So the movie is about the events leading up to that and all the problems that they had getting the dish working. Set on the backdrop of a quaint Australian town in the middle of nowhere, and all of their funny, quirky inhabitants. I challenge you to watch that movie and see if you can, how many connections you can make with what you've learned in satellite communications already. They talk about all these sort of technical terms with dish antennas. They talk about look angles. It's really interesting. So, anyway, a little digression. We used to have movie night as a class in satellite communications until it got too big and unwieldy to handle. Back when this was a lesser popular class, maybe 10 years ago. So one day I hope to resurrect that. But summer semester is a little bit too intense and compressed to have movie night. And my living room is a little too small. Okay. We're not done with inefficiencies. Let's list a couple more inefficiencies. Ohmic losses. This one's very straightforward. The dish is made out of metal. When the wave comes down and reflects off of it, it's going to excite currents on that metal that slosh back and forth. It's not a significant source of loss, but you can measure you lose a few percentage points off of the radiation efficiency just due to the fact that you didn't make the dish out of a superconductor. And you lose a little signal that way. And finally, spillover losses. And this is both for the reflector. This can happen for both reflector and subreflector. When you illuminate a dish antenna, remember what we said about antennas. Because of that very mathematical property of the Fourier transform, no matter how clever you are, you will never be able to make a feed element that has a perfect sector that fills up your dish and then has zero radiation out there. And so you're always going to illuminate a little bit of energy out in this region that winds up being inefficient. And likewise, even if you did have a sharp transition here, you can't have a sharp transition, and that's going to lead to diffraction. So some of the energy is going to spill over the edge and diffract into unwanted areas. Generally, the way to minimize spillover losses is to make an electromagnetically large dish. The bigger you make the dish, the less spillover losses that you have. The spillover losses accumulate one over, or basically with respect to the perimeter of the circle of the dish, whereas the gain of your absolute dish is the area. So gain goes up faster than spillover losses as you increase the size of the dish, and therefore the efficiency gets better and better. And of course, that also happens for the subreflector if you're using a subreflector configuration. As I said, a good dish probably has about 80% aperture efficiency. A mediocre dish, probably 70%. And if you really want to turn it into a $1 million research project, there are some really sensitive dishes that get up to like 90% in terms of their aperture efficiency. Hard to get beyond that, though. Okay. Any questions about dish antennas? Yes?
I was looking at the
Feedback dish was you were describing it, and it's got these jagged edges. Is that affecting anything?
The green bank. So you look at the picture, and it has some jagged type of edges to it. So my guess on that, I'm just going to hazard a guess. I'm not an expert on the green bank antenna. But oftentimes you use jagged edges like that to break up some of the diffraction coming off the dish. It tends to make a more uniform and more graded diffraction gradient. You'll see some of the same things on maybe boats that are stealthy, some jagged edges. I'm guessing that's why they do it. But until I do my ANSOF simulation at home tonight to answer that question, I will not be able to figure out why. Good question, good question. Any other questions? Yes, Evan.
You were talking about the inflatable dish antennas.
Yes.
How the solar
Radiation can still focus and burn your feed. That probably doesn't meet the route
Rayleigh Criteria in terms of the surface roughness, but it's still affecting its diffuse length.
That's right. Okay, that's a really good. This is a great question. So clearly, the question is, if you're at optical frequencies, the wavelength is going to be in the hundreds of nanometers, right? Clearly, that's going to be less than the Rayleigh criterion for this surface. Why does it burn up and reflect, most of the energy reflect with angle of incidence equals to the angle of reflection? Well, the answer is you need to get into the physics of paint and realistic-looking objects. So most objects, especially things that are painted, are actually multi-layered in their electromagnetic composition at some scale. So for example, almost every object, well, certainly every object in this room, any realistic object, unless you've done something very intentional to it, like silver the edge of a glass or something like that, is going to be diffusing. It's going to produce almost entirely non-specular reflection at optical frequencies. And we rely on that, right? If that weren't true, our world would look like a fun house. It would be a mess. But the fact is, I can look at that wall, for example, that's painted, and in just about every angle that I look at it, I can see it. And I see the color. And that's good, because that means that the surface is diffuse, and I can see it from any direction. Now, if you look at most realistic surfaces, this whiteboard is a really good example, because it's actually very smooth, but it's obviously very diffuse as well at the optical wavelengths, because if I look at it on the side, I can still see whiteboard. I don't see a mirror. However, if I look down at its kind of smaller scale, what I see is something that is very rough, and this is the diffusing part. And there's often a shiny veneer on top. Part of this is how we formulate paint. The reason why we formulate, if you think about paint, it's a liquid that contains a binder and pigments. The pigments in paint form kind of a rough morass, kind of a rough mass that all kind of binds together. The binder is either oil or latex and a solvent or something, and that tends to smooth over the surface. So that now you have sort of two different surfaces. You have a diffusing surface, and then you have something that has more, it's flatter and it's more reflective with some minor aberrations to it. And this top surface can often reflect specular light. The bottom surface has surface roughness associated with it that spreads out electromagnetic radiation in all directions. You have both of those modes present in an object. In fact, this is sort of like the hallmark of computer graphics. This is when you learn to write computer graphics code. If you want to have a career in the entertainment industry and program CGI, or you want to work for video game companies or something like that, you need some shader code to figure out how your 3D objects are supposed to look like, right? It's the same principle. You say, well, what do things look like? Well, if you use this two-layer approach to modeling things, what you find is that there's a diffuse component that no matter where the energy comes from, this diffusing layer is spreading it out in all directions. And this undulating component up here produces a specular component that, depending on how undulating this is, provides a sort of beam, so a spreading factor. So you hit it with a plane wave, and you'll get a bunch of plane waves that radiate out that are centered over a width. And that width changes depending on how undulating this is. And so there our entire models. I don't know if you've ever heard of the Phong Shading model. Do you know this? Have you ever heard that term in computer graphics? Phong was a grad student that invented this shading model from University of Utah, I believe, way back. And it's kind of sad. I think he died of cancer shortly after he finished his PhD. He was a brilliant guy, came up with this great shader code. And his idea was there are really three parts to modeling something. So let's say I had a sphere. Well, first, I have ambient light all around. I have my sources in the environment, for example, these lights that are showing all of my physical imperfections on the camera right now. But I also have a lot of ambient light. And so all appearances of things will be composed of three components. One is ambient light. And Phong Shader model says the world is so complicated, I'm just going to give it a uniform color. And I know that the surface is going to have this roughness here. So I'm also going to look at my sources, and based on that, making something called the Lambertian scattering assumption, which assumes that you have basically an added, your rough surface is almost like a white Gaussian noise. I'm going to impose the pattern that that would produce, and that usually results in a sphere. Let's say the light source is coming from down here. That results in a relatively uniform shading where as you move to darker and darker parts of the sphere, on the backside you get less and less. And so if you just did everything with uniform color, your world would look like The Simpsons, some crummy American animation where nothing was shaded. And if you add this component on top of that, now things start to have some depth, and they start to look interesting. And then the third component that you see is a specular component, where part of the Phong Shading model says, okay, this component here, there's going to be a width associated with any beam that strikes, a diffusing factor, so that that source that's shining in on here, I'm actually going to see angle of incidence equals to angle of reflection about a band of color, or about a band of intensity. So think of this as the shiny spot. So you add the uniform color plus the shaded color plus the shiny spot. These two are due to the multimodal reflections that are typical from the surface. And you get a very realistic picture of a sphere. Maybe I'll try to bring it in next class period to show you. As it's kind of interesting to see those. And the dish is the same thing. So if you look, I'm not picking on your hairline here, Evan, but like if you look at Evan's head, I can see these diffuse sources that are like, your cells are much larger than optical wavelengths, and that yet so you would expect them to diffuse everywhere. And indeed, you look kind of like a Simpsons character. But you also have these shiny spots on your head from the sources that are quasi-specular. Same thing with the satellite dish. You would probably make a great reflector antenna in some capacity. Okay, I'm done picking on Evan and making an example out of him. That was an excellent, insightful question. You need to take more EMAG classes and ask pesky questions like that. That's good. Any other questions about dish antennas or video games? I actually give this lecture. It's called the Electromagnetics of Video Games. And it's basically discussing some of the similarities. I think one thing I talk about is Phong shading. I talk about ray tracing and talk about how like one field has informed the other and back and forth. It's kind of a fun little lecture to give at special topics. If I have to guest lecture somewhere or do something for the student IEEE branch. The reason why I put that lecture together is I kept teaching all of my students this great electromagnetic theory. And they'd become experts at RF, antennas, and propagation. And then they run off and work for electronics arts, and I couldn't figure out what was up. And I realized, oh yeah, it's the same math. It's the same math. They're very transplantable. If you know EM, you can make, I guess, NCAA college football games or something like that. Yeah.
I was going to, last session we talked about basic antennas. And
Yeah.
I was wondering if you could just briefly describe a little bit how the RF tags work. I think there's an antenna somehow, vaguely I know that there's some transmission line theory that goes with it, how they work. And maybe you could
How RF, what works?
The RF tags that they put in books, they have little...
Oh, okay. Yeah, the RF tags that they put in books. So usually, in my experience, the ones that they put in books, like at what they call EAS, Electronic Article Surveillance tags, those are usually inductive in nature. They're little spiral antennas. They work down at HF frequencies, which is about 13.56 megahertz. And the idea, they tend to work in the near field, using near field rays, because at 13 megahertz, the wavelength is actually several meters long at least. But they don't really care, because ultimately RFID technology isn't about coverage, it's about location. And the nice thing about HF RFID is if you can read the tag, you know exactly where it is. It's right by the reader. So you put those little loop portals by your exit of your store, and if somebody walks out with the book that has the tag in it and the little inductive pickup coil, it'll trigger the alarm. That's mostly how the book tags work. Now, there's another class of UHF RFID tags that are used mostly in logistics, warehouses, and that sort of thing. Those tend to work at farther field distances, and they do rely on they're actually very interesting. They're using far field radiation, but they're actually not transmitting anything. There's a reader unit that illuminates them with CW waves, and then they reflect modulated information on that signal. How do they reflect modulated information? Well, an antenna, just by virtue of the fact that it's a hunk of metal, it has what's called a radar cross-section, like any other hunk of metal in space. That is a metric that we electrical engineers use. We measure it in meters squared. It's a unit of area. And it roughly represents the electromagnetic size of something, how much energy it grabs and then scatters back to a radar. These radar units are operating a lot like a radar. And it turns out you can change the radar cross-section of an antenna depending on what you connect to it. So if you connect an open circuit, it's like a transmission line, right? It reflects with 100% plus 1 reflection coefficient. If you do a short circuit, it reflects with negative 1 reflection coefficient. If you do open, short, you have a way to actually do phase shift keying on the reflected signal. And so it's a way to basically do RF without batteries, without power, basically. You just harvest a little bit of the incident energy, wake up your stingy little CMOS circuits, start flipping a signal back and forth, start load modulating your antenna, which you can do with a very simple electronic device. You got rid of your power amplifier. You got rid of your RF signal generation circuitry, all the expensive stuff that takes energy to do communications. The downside is that now you've got a radar link to deal with where the distances, where the losses are 1 over r to the 4th instead of 1 over r squared. So you have to do some tricks with your receiver to make it more sensitive and to work around that. But over short ranges, it's perfectly acceptable. So yeah, you can come to my office and follow up if you want to talk more about that stuff. That's a whole other course at Georgia Tech.